It's a pleasure to introduce Professor Amin Shokrollahi from EPFL, Switzerland, Lausanne, Switzerland. And I just write down some of his history. So, Professor Shokrollahi is from Iran and got his graduation in mathematics in Germany, and also his PhD in computer science in University of Bonn, Germany. He was assistant professor at University of Bonn, and then moved to the United States as a research fellow at International Computer Science Institute in Berkeley, and then was member of the technical staff of Bell Labs, New Jersey, again, the States. And then was back to Europe, Lausanne, EPFL, since where he joined in 2003. He's also some very interesting experience with enterprise. He was chief scientist from Digital Fountain Company. This company was sold to Qualcomm in 2009. And in 2011, he founded and is CEO of this Canton Boost enterprise, which is still running. And concerning some awards, I just list a very small of them. He got in 2002 Information Theory Paper Award for the best paper of the year. And he is one of the inventors of the practical eraser code Tornado codes, and the principal developer of the Raptor codes, which belongs to the class of rate-less eraser codes known as fountain codes. For this work, he got two very important prizes in 2007 from the best paper, again, from IEEE Communication Society, and the Eric Summer Award also in 2007. In 2012, he got some very important prize again, this Richard Hamming Medal, together with Michael Labie. This prize was award for the conception, development and analysis of practical rateless codes. I think this somehow summarizes some of Professor Amin's biography. Okay, it's really a pleasure to have him here. Thank you.
Thank you very much for the invitation. And one of the things that we didn't mention is that I have strong ties with Brazil, because I have family here, and this year is actually the 30th year that I travel to Brazil on a regular basis. So I could say qual é pessoal. All right. As Swedi mentioned, I am actually right now only at CANDU Bus, and at EPFL I'm on a leave of absence. So most of the work I will be talking here about is done in collaboration with engineers of the CANDU Bus team. The problem that we want to discuss is that of communicating bits between two integrated circuits or chips. The communication is along electrical wires, so you use electrical signaling in order to send the information. It's not wireless. And the task is, yes please?
Please explain the name of your company.
Oh, CANDU. The Iranians here probably know the name. It means a beehive. And in fact, very, very interesting. The reason we chose the name was because the communication wires help one another in recovering the data. So that's why we call it CANDU. But of course, in English, it means can do. And interestingly, there is a word in Japanese that's kando, which means exciting or smart. But we didn't know when we chose it. And as with many other names, like Raptor codes, it was chosen by my wife, who is perfect in doing this kind of stuff. So, but she's German, even though the name is Persian, so you can imagine. Anyway, so that's the task. There are many, many examples of chip-to-chip communication, and I'm just going to talk about very few of them. This is one example where you have DRAM dies stacked on top of one another, and people drill holes, nano holes into these DRAM dies and connect them with silicon vias. It's absolutely amazing, mind-boggling that's technically possible, but it is possible. And these dies communicate with the base layer, which is a logic layer sometimes, or maybe in some other process. This is really not science fiction. It is being produced today. And here is a sort of a picture of one device like this. Now, so the communication inside this DRAM is a sort of chip-to-chip communication, but then you want to get the data out. So this goes typically to something called a controller. The controller is a sort of smart piece of logic that does a lot of things, like taking the data out of the DRAM, writing things back into the DRAM, communicating with the outside world, etc., etc. Typically, it's in a very different sort of process because you want it to be fast and have several other processes. The communication between this DRAM, stacked DRAM die, and the controller that usually goes through some kind of a medium, could be a silicon interposer or something else. This is another type of chip-to-chip communication. Now, all of this could be a memory system. The whole thing here could be in a package. So you couldn't even see the different things. You see a package. And this could be connected to some other device, for example, a processor, using a completely different substrate over here. So the physical properties of communication here is very different from those here, and again, very different from those here. So there are. I just gave a very few examples. I mean, there are many. There's about the applications are abundant, and the thing is that connection speeds are increasing, but the real estate on the chips are not increasing. The paths from which you have to launch the signals, they are the pitches of these paths is fixed. You cannot change it. So really, you're sending more and more bits across a given wire. So you need to transmit more and more bits across every wire. If you look at one of the biggest storage companies in the world, EMC, they say that the amount of data doubles every 1.5 years. So if the amount of data doubles, there is more stress on all parts of your communication system, including the chip-to-chip communication. So you can see it. By the way, in wireless, the amount of data is much more than doubling every 1.5 years. So very typically, when you want to look at situations like this, you want to know what is the communication channel, right? So the noise, and here you really want to know what is the nature of noise on the signals that you're transmitting. I will tell you maybe a little bit more, what the signals are. Those of you with some electrical engineering background, which by the way I don't have, will know, a little bit how this signaling is done electrically. But I will talk about it also a bit. So there is noise. The point is that there is noise on these, in this communication channel, and because there is noise, you will not receive the same information as you were intending to send. We know that. But what is the noise? Well, let me tell you what it is not. It is not. It's nothing even close to the noise you find in a wireless system, or in a DSL system, or in magnetic recording, or practically any other communication system that you've seen or heard of. It has these communication systems all have a lot of what we call random noise. On the other hand, the communication system that we are talking about here, practically all the noise in that system is deterministic. However, you are extremely limited on resources, really extremely limited. There is a rule of thousands in terms of throughput, energy that you want to spend per delivered bit, and the recovery time for it. In wireless, you're typically talking about megabits per second. In chip-to-chip, you're talking about gigabits per second. When I'm talking about megabits per second, I'm not talking about the whole system transferring megabits per second. I'm talking about sort of each individual line transferring megabits per second. Here, you're transferring on every wire multiple gigabits per second. It's about 1,000 times higher. The energy per bit in the wireless world, in a lot of parts of a wireless system, is measured in nanojoules per bit. So 10 to the minus 9. Here, we are measuring it in 10 to the minus 12 picojoules per bit. In fact, I will show you some systems that we're developing where we are in the realm of femtojoules per bit, so which is 10 to the minus 15. The recovery time per bit. In a wireless system, it's good if you are within a few nanoseconds. Here, you have to be within a few picoseconds. Again, 1,000 times lower. The recovery time is 1,000 times lower. The energy that you can spend is 1,000 times lower. And the amount of data you want to send, paradoxically, is 1,000 times higher. How do you do this? So when you talk about noise, you have to talk about, well, you really have to talk about noise. What are the noise types you're seeing? There are many, many different noise types, and I've just gathered a few of them. Well, these are sort of the most important ones, anyways. So there is something called a simultaneous switching output noise, and I'm not going to ask you later what these things are. I'm just going to give you sort of an overview of what. So the SSO noise is you get it when something like this happens. So you have a source from which you draw current or energy in order to send the signals. If the amount of energy that you're using depends on the signal you're sending, then you're taking energy out of that source in intermittent fashion. And this creates problems for the entire system. This is called SSO noise. Sometimes you want to recover a signal by comparing it against a fixed reference. If the reference moves, you will have reference noise. Crosstalk is really difficult. I mean, you have these wires in close proximity. If you really need to make the wires in close proximity because you don't have much real estate. But if they are in close proximity, the signals that you send on one wire couple with the other wire and create noise on those other wires. This is called crosstalk. Electromagnetic interference. A lot of you know when you get on a plane, they tell you, you're not supposed to have your phone in, whatever. Right? It used to be that you couldn't even turn on your electronic devices. This is because they are, for the most part, they are scared of the EMI noise. So, because when you're sending data at high speed across a wire, essentially the wire becomes an antenna, even if it's a very short length. And so these signals are going to propagate and couple into other devices, and you will have trouble. If you are an antenna, there is also the inverse thing, because the signals from the other devices couple into your signal. There's noise. Common mode noise. So, for a lot of reasons, the amount of voltage or current that you're sending on the wires can simultaneously go up and down. And again, this causes problems. Intersymbol interference, by far, the worst noise type in this world is intersymbol interference, and I will talk about it. And thermal noise. If you kind of, I just put here some numbers. Don't take them, take them with a huge, huge grain of salt. These numbers are not necessarily absolutely correct, but let's say the various noise types and how much they contribute to the system is maybe about this. But what is really interesting is how much of it is deterministic and how much of it is random. 99%, I would say, is deterministic noise. So here is the problem. You know exactly how this is going to work out. You know exactly your channel. It's like in a wireless system in which you exactly know your channel. The problem is you have neither the time nor the power to correct it. You're completely limited on resources. That is the issue. All right, so there are several ways of mitigating noise in such systems. The SSO you can mitigate by having a different type of modulation of signals on the wires, or by the design. So, for example, you could shield your wires so that they don't talk. There's no crosstalk, or you can put them a bit apart. This kind of stuff is possible. The reference noise, again, modulation. The SSO is really by design. The crosstalk is by layout. So, how far you can take the wires apart. And so on and so on. There are various ways that the industry has tried to mitigate these noise types. Keep in mind, though, that the stress on the systems is increasing. The faster you send your signals, the worse these noise types become. For example, in backplane links, you have you're sending data at a rate with a clock that's running at 28 gigahertz. So on one wire, you're sending data at 28 gigahertz. If the wire is there are parts where the wire goes out of the chip and goes into a PCB board, and there's just a fraction of a millimeter of that wire is open. This thing becomes an antenna right away, and people are just pulling their hair how to deal with electromagnetic interference on these things. So people have found ways to mitigate them, but these ways are not going anywhere really. As the speeds are increasing, you will have issues. All right, so you will see that a lot of these ways of mitigating deal with modulation. The right modulation can mitigate a lot of these noise types, and that's what I'm going to talk about. So what are current modulation techniques? What people typically use is called NRZ, or non-return to zero signaling. So if you're sending binary signals, you may think of a high-level voltage as a 1 and a low-level voltage as a 0. And it's called non-return to zero because you make a transition from the state you're in, rather than going to a mid-level and waiting for the next signal. High-speed systems have to be non-return to zero, because otherwise you lose time by going first to mid-level and waiting for the next signal. So this is sort of an example of sending a sequence of zeros and ones. It's called, as I said, non-return to zero. This is what is going on the wires. But how are you going to, specifically how are you going to make the modulation? We will see. Here is a simple receiver, and for those of you who actually have an electrical engineering background, do bear with me, because this is really taking out a lot of the complexities of the system. But that's good enough, I think, for now, for what we want to do. So there are bits that are coming in, and I'm thinking of bits as being plus or minus 1. They go into something called a driver. The driver actually does the physical implementation of sending those voltage levels on the transmission bits. And on the receiver, this is by the way called signal-led signaling. On the receiver, you have something called a comparator. The task of the comparator is to compare values on its two legs. So one leg of the comparator is connected to the wire. The other leg is connected to a reference. The reference could be the sort of 0 in this case. And what the comparator really mathematically outputs is the sign of the difference of the values on its two legs, plus 1 or minus 1. So this is called signal-led signaling. So if you think of signal-led signaling and how it could sort of move in time, so you have 2 points, plus 1 and minus 1. You have a distinguisher. And then, these, as you transmit the data, these things move. And whenever they cross a distinguisher, you will have an error. Signal-led signaling is used in many sort of low-speed systems. This is really the start of doing sort of electrical signaling in the first place. And this is sort of a summary of how it behaves in terms of various types of noise. In terms of SSO, it's really bad, because it actually uses different amounts of power for 0 or 1. It has a reference, so if the reference moves, it's going to have problems. EMI. I mentioned just now that if you send high-speed signals on a wire, it becomes an antenna. So if you don't do anything else other than that, it has EMI issues. It has common mode issues, because if all of the wires in your system go up, then the reference is not going up with those wires. You will make an error. In terms of intersimilar interference, it's okay, but it's not good for very high communication systems. So already in the early 20th century, people came up with something called differential signaling, not because they had really high speed, very high speed signaling, but for other reasons. Here you are saying, what you will do is you say, well, why don't I spend 2 wires for 1 bit? And I'm going to send complementary bit values across the 2 wires. So a bit that I want to send, I send as B and minus B across these 2 wires. And the comparator is going just to take the difference between these 2 wires, right? And so you take the sign of x minus y. If there is no error, you get sort of the sign of 2b or the sign of minus 2b, you're good. If there is error, certain other things will happen. This is a really good system. So in terms of SSO, it will not have problems. The amount of power you need for bits, whether you send a plus 1 or minus 1, is always the same, because you're injecting always a plus 1 on one of the wires and always a minus 1 on the other one. There is no reference, so no reference loops. There is no EMI. Well, there is EMI, but I will get to that. Essentially, the electromagnetic far field that is created by one of the wires is kind of canceled by the other wire, because it's in close proximity. There is no common mode. If everything moves up and down because you're taking differences, it doesn't matter. But if you are in a situation where you're pin limited, So the number of pins is the same as the single-end signaling. You have to run with a clock that is double the rate. And this causes a higher intersimilar interference. So, practically anything, it's the bread and butter of high-speed signaling, differential signaling. Your phones are using it today, right? Your servers, many of your computers, actually the link to these, in my laptop, the link to the monitor is using differential signaling. It's really the bread and butter. But as the speeds grow, because your clock rate has to be double of what you should have, it will encounter problems. So, why can't we lower the frequency? Or how could we lower the frequency? One immediate thought is, well, differential signaling is only distinguishing between 2 levels. What if I distinguish between 4 levels, or 8 levels, or 16 levels, right? I mean, people do that in communications. Why not? Well, good luck, because this is going to kill you because of intersimilar interference. But anyway, so this is, I actually already said it, but that's fine. The other version, really, intersimilar interference is going to have a problem. And SSO is also going to have a problem with these things. The other version is to say, well, look at differential signaling. It's pooling 2 wires together. What if we pool more than 2 wires together and send correlated signals across more than 2 wires? This is kind of the coding theoretic, if you will, thought, right? You pool resources together, and maybe through that you can do a lot more. And this is what we call chord signaling. So I'm not going, by the way, in this talk, you will neither see formulas, nor will you see proofs, none of that. It's really a very high-level talk. Maybe to some extent because I'm really not interested in that, in this particular. So I'm going to show you how to arrive at sort of a new type of coding theory. What I will not be talking about are constructions, solutions, test chips that we have, and all the electronics that are behind it. Most of the thing is because I don't know much of the electronics behind it. So it's the engineers that can do bust with it. I can probably fool people for about half an hour, but that's it. So let's take a look at what's happening. So if you look at 2 independent wires with single-ended signaling, and you look at all the values that you can send across those 2 wires, you do agree with me that there are 4. They are the combinations of +1s and -1s. Now, think of the simultaneous values of these wires as points in a 2-dimensional space. So that's the abstraction. So, in single-ended signaling, you had essentially points in 1 dimension. And now if you have 2 wires, you have points in 2 dimensions. These are the points you're sending. And if you look at one of the comparators, the first comparator, it's distinguishing, let's say, the y values of these points. So it's a line, right? Now with this distinguisher, you certainly can distinguish points that are on the opposite sides of the line. But you certainly cannot distinguish points that are on the same side of the line. So at least you should be able to distinguish these points. Once you receive them, you want to know, what point was it. And well, it's very simple. You add another distinguisher here, right? And now you are, this is the second comparator on the 2 wires. And now you can completely distinguish these points. So essentially what you've done is you have now subdivided your space R2 into 4 disjoint regions. And the regions are defined by these distinguishers. And each point in this region is uniquely defined by a signature. So this is plus, plus, minus, plus, etc., depending on what sides of the distinguisher they're on. So, once you see this, you say, well, fantastic. Let's look at, if I have n wires in my system, I can think of the simultaneous values I'm sending on these n wires as points in the n-dimensional space. And I need sort of comparators to distinguish them. Perfect. So here's an example. You have 3 bits and 2 wires. So, what better way than distributing the 8 points, which correspond to the 3 bits, in an equidistant fashion on a circle, for example. So here are the points. And here you need 4 distinguishers to distinguish the points. These are the lines. And this subdivides the region into 8 disjoint regions, or chambers. And if you really want to sort of make it into something somewhat practical, it turns out it's actually better to shift it by 22.5 degrees, clockwise. And then you need sort of the equations for these distinguishers becomes very simple. This is y, this is x minus y, this is x, and this is x plus y. And every point is given by a signature vector of 4 signatures. Right? And then you can sort of have some kind of a bit mapping to these points that is somewhat efficient. And this gives you kind of a code, if you will, of values. So the code consists of and I really need to say that right away. The code consists of the points plus the comparators that distinguish the points. It's not just the points themselves, but also the comparators that distinguish them. This is really important because the comparators essentially give you a method of decoding. So you want to have the efficiency of the code directly embedded into the definition. All right, so those of you who like electronics, so you see a little bit now here. So how does that now work in a system if you wanted to actually implement it? Well, typically there is a digital part of the system. It's called a digital encoder. So 3 bits go into this encoder. 3 bits go into this encoder, and out come 8 bits. These are control bits. And you will see this is a very simple encoder, as you can see, with a few gates. And what are these control bits? What the control bits really do is they turn on and off transistors. That's all they do. The transistors, they're connected to sources of various strengths. Obviously, a strength of square root of 2 minus 1, obviously you cannot do in a practical system. So, think of it as what, 1.4, if you will, and 1. And then they're connected to sinks of various sources. And every one of these bits, what it does is it instructs the corresponding transistor to open or close. And by orchestrating them the right way, you get exactly the right signals across the wires. So, for example, and then there's the same thing for the second wire, and the control bits for the second wire are different. So this is sort of in a practical, by the way, in a high-speed practical system, you would not do it that way. There's a lot of sort of other stuff around it, but this is kind of the philosophy behind it. So there is a digital part that does the encoding, and then there is the it creates these bits, the control bits. They open and close transistors, and then with them you can actually get the right values on the wires. So once you got the values, what happens? So this is on the receiver end. Well, there is typically a piece of electronics that does a bunch of things like equalization, ECU, and so on. And once it has cleaned, so the task of these guys is to clean up the signals a little bit at least. And then it goes into a network of comparators. The comparators, the 4 comparators you see here, are the 4 lines that distinguish the 8 points. It's just the electronic version of it, if you will, right? And so now out of these comparators you get 4 bits, but you're actually interested only in 3, right? So you have to do something to these 4 bits to get the original 3 bits. And so sometimes there's a decoder. In this case, the decoder is very simple. It's just an XOR of the last 2 bits, while the first 2 bits, or actually the XOR of bits 3 and 4, while bits 1 and 3 just go unaltered into the system. And here are the 3 bits you want. That's pretty much it. And this is the general setting. So bits go into an encoder. This encoder is a piece of digital logic. All this stuff over here is in analog. It's sort of you need analog circuitry to do it. And then oftentimes there's a decoder over here. That's again a piece of digital logic. If you think of differential signaling, it's a special case of this. The encoder, what it does is actually negates the bit. So when a bit comes in, it gets negated. The bit and its negation go over 2 wires, and then there is sort of the RX front, and there is only 1 comparator, and there is no decoder. All right, so what are the parameters? You have n is the number of wires, which is the dimension of the space the code words reside. Then c is the number of comparators. And then you can ask yourself the following questions. If I'm in the n-dimensional space and I'm allowing for c comparators, what's the maximum number of chambers I can have? Which means the code words that I can distinguish from one another. What's this maximum number, capital N? And fortunately, this was already answered in 1974. It's called Zaslavsky's formula. And this is the formula. Actually, not too hard. You know, the Slavsky's formula is in a much more complicated setting. I just took a special version of Slavsky's formula here. So there's no disrespect to Slavsky, because this formula can also be proved in an easier way. Okay? All right, that's fantastic, because then you can tabulate. Right? You can say, all right, if I have, I don't know, 4 wires, and I'm allowing for 8 comparators, what's the maximum number of bits I can send? Well, it's 7, turns out, because 128 is 2 to the 7. So you can send 7 bits on 4 wires with 8 comparators. In terms of number of comparators, you're not that bad, because the minimum number would be 7. You're just spending 1 more. It's 8. And yes, please.
So when you increase the number of bits on wires, you can reduce actually the clock frequency, right?
Yeah. So the question is asked. So the first part is because you're reducing the number of bits on the wires, you're reducing the clock rate. Yes.
So it's going to be better in terms of ISI. But your point is
not necessarily. So I will tell you. You know, just bear with me. You will see what's happening. So right now, what we did is we sent more bits. You know, you remember my previous thing? You said you want to send more bits per wire. Oh, fantastic! Here I'm sending almost 2 bits per wire, but you know there is also the other way of sending 2 bits per wire by taking a PAM4. Why not take a PAM4? What's the difference of this between this and PAM4? So clearly there is a bit, or there is a part of the theory that's still missing, and I will get to that part. Because what happens to noise? That's the question. All right. So I'm just comparing to 4PAM, which is sending 2 bits. But think of 4PAM. You know, whatever is bad for 4PAM is even worse for 8PAM, etc. So 4PAM, we said, has problem with SSO, you know, EMI and comm mode, etc., etc., etc. The quartz signaling, you can orchestrate it in such a way that in terms of SSO, it's worse than PAM4. In terms of EMI, it's worse than PAM4. In terms of common mode noise, it's worse than PAM4. Maybe in terms of ISI, it's better because you're sending more bits. Maybe. It's not clear. So far, I've been leading you down a path that's not necessarily that great, right? Because this one is just so much better. Okay? But this is obviously not the end of the story. Okay. Now, again, so this is back to your question. Does reducing the frequency help? All right, so now I'm going to show you certain things that you may or may not have seen in an electrical engineering background or not. It's called eye diagrams, and I will try to explain what they are. What you see here is a channel, and this is the frequency response of the channel. So it tells you, essentially what this tells you, and this is in dB, it tells you if you send a signal with a certain amplitude, and you're sending it at a certain frequency, by how much does this amplitude get lower? Right? If you have, for example, if you have 6 dB loss, or minus 6 dB, this means it gets halved. Sometimes, you know, we work with channels with 35 dB loss, where you know, things, essentially there's nothing left, but you still have to recover, right? So here is a channel, this is really a mobile memory channel, etc. And we want to send 8.4 gigabits per second per wire. All right. If you use single-ended signaling, and I'm just looking at, because, you know, I'm just looking at the first 2 wires, just for simplicity. What you get here is an eye diagram. What is an eye diagram? Okay? Think of it that way. You're sending signals, which, you know, originally you're sending these nice rectangular shaped signals. And by the time they receive at the receiver, they're received at the receiver, they become something, you know, like a sinusoidal, or, you know, something different. It could be something like that. And then you look at signals in succession. You say, you know, I want to look at 1 million signals that I'm sending randomly. And because there is intersymbol interference, etc., the signals that you send, they, you know, some of these signals may just look like this. So the signal that perfectly looked like this at the start of the transmission becomes a signal that just looks like this. Okay? And what you want to check is this thing bigger than 0 or smaller than 0? And oftentimes you get some opening over here that tells you if I sample the signal in this opening, I'm not going to make a whole lot of error, right? So what this diagram is if you sampled everywhere here, you would have an error of, you know, 10%. Down here, maybe it's 10 to the minus 15. So it's really an error probability plot that you see.
So the more often the better.
The more open, the better. So this guy over here is about 36 picoseconds wide. I mean, it's a very small amount of time, which means at most, you have this much time to recover your signal. 36 picoseconds. That is 36 times 10 to the minus 12 seconds. It's very little time, all right? The vertical opening that you see here is about 27 millivolts. So the vertical opening, the smaller the vertical opening, the more sensitive your electronic equipment has to be in order to detect the signals. So essentially more powerful. And one of the other things that people look at is if you had a perfectly shaped signal, how much of that signal is lost, or how much of it can you get back in terms of horizontal opening? And it is about 30% in this case. All right, so now we go, so this is something people knew. Now we go to, I don't know, the 6, so I didn't show you the hexagon, but you can imagine how the hexagon looks, like 6 symbols. So because you lowered the clock, your signals are now here. And what previously you had 36 picoseconds, here now you have 135 picoseconds, less 22 millivolts, and only 23.5% of the UI. 23% of 0.5% of the UI, the UI is the unit interval. This is bigger here because your signal, the clock rate is lower. And still you get even smaller. It doesn't look that good. You go to the octagon, you recover a little bit of the horizontal opening, 38 picoseconds. But it's really, in terms of its own UI, it's even less, and 22 millivolts. So here's the comparison, right? This is similar signaling in terms of vertical, horizontal, and sort of percentage opening. And you look at this, and you say, who in their right mind would take any of these guys if this is already there? And this is all the same throughput. So again, I have led you to here and showed you, we can't do anything better than people could do before. Or can we? So here's kind of the trend. It's really not that great. Now here's the discussion. What is happening really is that as you pack more and more points on the wires, the chambers become smaller and smaller. And so the code boards become more susceptible to noise. So it sort of moves around, and there's a higher probability of leaving its own chamber and making an error. That's really what's happening. And this is something you can't really change. I mean, the chambers will become smaller if you send more signals. The only thing you can change is the ability of the signal to move around. You want to really limit the noise as much as you can. And now, if you look at the system we are designing right now, and you looked at these guys over here, this is what we get. As you can see, this is obviously much, much better. So how was this designed? What did we do? What kind of ideas did we use to design this? This is, by the way, for a mobile memory system, for a next generation mobile memory system. It's really the intersymbol interference. As I mentioned before, by far the worst noise type here is intersymbol interference, because you cannot do something that we call equalization. You cannot really correct for it, because you neither have time nor do you have the power to do it. So what is intersymbol interference? You see, you're sending these perfectly shaped rectangular signals, and by the time they arrive, they kind of smear over. They sort of bleed into signals that were sent before, paradoxically, but definitely also bleed into signals that were sent after. So really what you're getting is this. Now you want to make a decision on this interval over here. So you want to make a decision, you want to check against 0. What you have to do is you just have to add up these signals, because they came together. Once you add them up, this is the signal you get. And here it's bigger than 0, so you make an error. This is why intersymbol interference is so bad. As if the signals bleed into the previous ones, they just make things difficult. They make things more. Now, here is the missing link. I showed you, chambers and so on. The missing link, the analog, if you will, of the minimum distance for coding, is what we call ISI ratio. And I will show you what happens. Really, the geometric interpretation is the following. Let's say in the previous instance, you sent this signal, and you're comparing against this comparator over here. The thing is, the further a signal is away from the comparator, the more pull it has on the signal, the next signal. Because really what is still on the wire when you look at the signal is the distance of this signal from the comparator. So the more away it is, the more of its effect is still on the wire. The more of its energy is on the wire. And this is going to pull the next signal. If the next signal is very close, it can be pulled over the comparator to make an error. That is really what's happening in this system. And so this gives us a figure of merit. It's called the ISI ratio. The ISI ratio for a code, again, a code consists of the code words and of the comparators. So for a given comparator, the ISI ratio is the ratio between the distance of the furthest point from that comparator to the closest point to that comparator. In this case, the higher the ISI ratio, the worse it is. The worse the code is. So, you can then start running experiments. Here are two completely different codes. This is operating on 3 wires, this is operating on 2 wires. The only thing they have in common is they have the same clock rate. And you see they have the same ISI ratio, and they have roughly the same horizontal openings. Here are 2 other codes. This is one, this is the octagon. This is actually the PAM4 code, or the 4-PAM code. The 4-PAM code has an ISI ratio of 3. This guy has an ISI ratio. By the way, the ISI ratio doesn't need to be an integer or even rational. Give me the irrational number. Here it's 1 plus square root of 2, right? So this is a smaller ISI ratio, and the eyes are still kind of open. This tie-dye thing here means that's actually closed, so don't worry about that. The eyes here are closed. Here still they are kind of open. I mean, no practical system would ever be able to deal with it, but it's still sort of theoretically it's open.
Sorry?
Yes, please.
Is the eye always square root of the dimension plus 1?
I'm sorry?
Is the ISI ratio always square root of dimension plus 1?
No.
Because it's dimension 4 and it's 3. I thought it's 0.
Well, the dimension here is 3.
Oh, it's 3.
It's in a 3-dimensional space.
Oh, I thought it's 4.
No, it's much more complicated. It has to have to do with the code. It cannot be just a dimension. All right, so okay, so if you design the code right so that the ISI ratio is small, you can get rid of the ISI. So finally we found something where it's better than 4-PAM. God, you worked so hard, right? But all the other guys are still in the red. It's not that good. So what about all these other noise types? There is one simple trick that makes all the other noise types go away. One trick. It's incredible that actually exists. And here is the trick. So what is common mode noise? So you're sending signals, and all of the signals go by the same amount up or down, right? This is bad for signal integrity. You want to sort of make sure that this doesn't affect you. So what you need to do is that your comparators should reject common mode. So if you think of the differential comparator, it just takes the difference between these two. So the x cancels out, so the common mode goes up. So your comparators need to reject the common mode. What it really means is that the all-1 vector should be in the kernel of this comparator. So it should be orthogonal to the all-1 vector. So if you don't have anything in the common mode, if you want to reject the common mode, then it doesn't make sense to spend energy in that component, in the common mode component. So you don't want to spend any energy in the common mode component either, which really means that the sum of the values on the wires should be 0, or should be a fixed number. Let's say it's 0. That's really what it is. Which means the common mode component is along this vector, and so this has to be 0. So let's take a look how we can get differential signaling again. We don't know. Yes, please.
Does it mean that you code inside the hyperplane?
Yes, exactly.
Oh.
You code inside the hyperplane. Yes. So look at the differential signaling again. And this is really what differential signaling is. You send -1 and +1, and this is the comparator over here. Right.
Isn't it just the reducible representation of a set?
So the question is it the reducible representation?
Irreducible.
Irreducible representation? Not really, no. You will see that in a minute. You'll see that. So how do you get differential signaling? You start with single-ended signaling, and then you just turn this thing around. You apply an orthogonal transformation to the signal and the signal in a reasonable fashion. So what is that reasonable fashion mean? We call it a tempering orthogonal transformation. So if this is your orthogonal matrix, what you need to have is that the sum of all the columns of this matrix be 0 except in one position. That's all there is. And then if you have a matrix like this, an orthogonal matrix like this, you can take the original code words, put a 0 in front, and multiply it with this matrix. You can take the original comparators, put a 0 in front, and multiply with this matrix. And then you have something that is, interestingly, immune to common mode noise, has very good EMI properties. If you design the matrix properly, I'm not going to talk about has no SSO noise, etc., etc. This one simple trick does that.
Is it like having a parity check symbol?
Not really. No, it's much more complicated than that because you have this full orthogonal matrix. But you definitely are spending one more wire on which you're not sending anything. Which makes sense. I mean, you're losing a dimension, right? You don't want to send along the common mode. So at least you need to lose a wire. That's for sure. But this is the way where you don't lose more than one wire. You just lose. And if you think about differential signaling, you're losing one wire, but it accounts for a lot because you have only 2 wires at your disposal. So you're sending at half. But you could have something where you send 8 bits on 9 wires, where this additional wire does really come into the game. So here is a possibility. Take the Hadamard transform. And this is kind of the comparator network for that. And this gives, with this you can send 3 bits and 4 wires, which is already pretty good. We call this the ensemble NRZ, and we are actually trying to make it into standard in many different ways. So the common mode disappears by construction. The reference noise disappears again by construction. You don't have any reference in this system. The EMI kind of disappears. It's largely mitigated. There's actually a very nice theory, add-on theory, that I'm not going to talk about, how to do the EMI. It's actually very similar to what people call spectral null codes. But anyway, I'm not going to talk about it. And then the SSO can be also completely mitigated through the construction. So now, all of a sudden, we are much, much better than anything else. So this is really can be used in a wide range of practical applications. All right, so those of you who wanted to see a definition, here's one. here's a definition. It's not, I myself am not that interested in that, but because, and I will tell you in a minute why. But anyway, so it's good to actually fix it. So we call it a Chordal code. It has multiple parameters. This little n, capital N, C, and I. And it's a tuple. You have a subset of -1, 1 to the n of size capital N. This is the number of your code words. Lambda, these are your comparators. These are linear forms. That's why the lambda was used. So linear forms on n dimensions, C of them. There is something inactive. I didn't tell you anything about that. This is not so important. But what is very important is that you can distinguish any 2 code words through one of these lambdas. So for any 2 code words, we find a lambda such that if you evaluate lambda in C1 and multiply it with C2, so you get something less than 0. So they have different signs. And the ISI tolerance tells you that the ratio between lambda of C1 and lambda of C2 should be less or equal to I for all C1 and C2. This is kind of, there are, the reason I can tell you why I don't like this the definition. Because in a practical setting, you need to put so much more into this than just that. This is just the tip of the iceberg. And that's why I don't kind of, the minute you start writing this definition, people start, okay, I can build this, and this. And most of them don't work because there's a lot of other things that I've spent under the rock. That's why I don't like it. But you gave it names. There is ISI ratio, there's a detection complexity, there's number of code words, number of wires. You can think of the number of bits you send per time interval, which is the binary log of capital N, number of code words, divided by the number of wires. You can think of it as the rate of your system. Right? I'm sorry?
Can it be more than 1?
Oh yeah, of course. So yeah, there are some trivial bounds. You know, the detection complexity has to be at least, and the actually this is wrong. It should be at least log 2 of n, log 2 of capital N. Sorry about that. I don't think you have these slides in your, fortunately, because I had not tested the slides yet on any audience. So this should be log base 2 of capital N. The ISI ratio cannot be less than 1, and Zaslavsky's formula, you know, says something about the number of them. So there are examples of ISI ratio 1. The hypercube has ISI ratio 1. And it has exactly 2 to the n minus 2 to the n code words in n dimensions. Can we have more than 2 to the n code words in n dimensions with ISI ratio 1? That's an interesting, somewhat practical question. I believe no, but so on 2 wires, it's actually nice you can sort of draw pictures. These are really the optimal ones. So the optimal ones are really the equidistant ones. And you can see how the ISI ratio grows as you increase the number of code words. The fundamental question is, if you have the dimension and the number of code words, find the smallest I such that there is a code with ISI ratio I, obviously. A lot of people, when I talk to them, they talk about asymptotics right away. What if little n is large? And I just, frankly, I cannot stand it. Because, there's no practical system in which capital N is large. I'm talking about capital, small n's of the size 4 or 5. Not, anything larger than that is still, there is the theoretician in me thinks, okay, so what can we do? I think there is an upper bound, which is this, log base 2 of 1 plus I. This kind of should remind you of a capacity formula of some sorts, but I don't know whether it has anything to do with that. And, I think that this is an upper bound. I haven't proved it, but I'm pretty sure it is. And for large I, for integer values of I can actually get to that upper bound. But again, this requires you to sort of simultaneously route thousands of wires, and nobody does that. By the way, a lot of people also ask me, how about, what does information theory tell you about the number of bits that you can actually send? My answer is, unfortunately, it's inadequate for this setting. And at least the information theory I know, and I'm really not an expert. And I think the reason, I can tell you the reason. The reason is, when you look at these systems in which information theory has had a lot of impact, the actual power consumed is consumed in sending those bits. Think of a wireless system. The amount of power you need to send those bits by far is so much larger than the amount of power you need to detect those bits, that really the amplitude of the signals when they are received at the receiver, this is really plays the major role. If you look at information theory in this setting, it tells you very clearly you need an OFDM system. Implement an OFDM system on chip to make it happen. But the amount of power you need in the circuits to do the detection is so much more than what you put on the wires that it's really impractical. But in terms of information theory, we are orders of magnitude less than what an OFDM system predicts. So that's a bit of a thing. There are lots of constructions. There are group theory constructions, recursive constructions, constructions from spherical codes. I don't know. I mean, we have over the last 3 years, we have just amassed a lot of tools to construct these things. Here is a very concrete example. If you're in 3 dimensions and you want to put 16 points in the 3 dimensions, what's the best ISI ratio you can find? So one of the things we have developed are actually search algorithms and so on, using sort of combinatorial optimization techniques and so on. And but it's not clear that you find the optimum. So far what I found has 2.39 using 11 comparators, which by the way is very, very impressive. All right, so theory of these codes is subject of a much more technical talk than So here's an example. So we obviously we want to make these things into standards so people are using. So here is one example of a channel, of a backplane channel. And you want to send, you want to send 21 gigabit per second per wire. If you use differential signaling, you would see a channel loss of about 50 dB. If you don't know what it is, just believe me, it's impossible to do that. If you use ENRZ, you're about 35 dB. And if you use PAM4, you are about 29 dB. So one of the things I always want to tell people, already looking at a diagram like this, is you look at a diagram like this because you think of a wireless system or you think of a DSL system. Because this tells you a signal that had this much amplitude, after it goes through the transmission, has only this much amplitude. But the amplitude of the signal, the vertical amplitude in this setting, is not that important. What's really important is the horizontal amplitude, which, again, in systems like wireless is not that important. You cannot see it from something like that, but since people are used to it, I'm just going to use it. And here are sort of the eye diagrams. For the PAM4, and this is ENRZ, equal throughput. PAM4 is running at a lower frequency. The opening that you get is about 10.2 picoseconds. The opening that you get here is more than twice as much, even though this is running at a higher frequency. This is really the power of the construction of the code. And that's, this is what we go into standardization meetings with to show. But then people tell us, have you actually implemented it? We say, well, not yet. And the reason is to actually implement this chip will cost us about $5 million. So you tell them, give us the money, we'll do so. When you grow up, you come back.
What's the typical feature rating in this system?
What you want in a backplane system is 10 to the minus 15. In other systems, in a memory, in a mobile memory, is 10 to the minus 12. But what I'm actually quoting here is for 10 to the minus 15. And here is, so we used actually the whole sort of set of tools that we've developed to actually have this thing, which is called glasswing, the glasswing technology. So the full design is here. So I swept, as I said, I swept a lot of things under the rug. So you're given little n and capital N, you design code. The ISI ratio should be as small as possible. The spread of the L1 norm of the code word should be as small as possible. The coordinates should sum up to 0. The absolute value of the derivatives of the code word at 1 is small. This has to do with the EMI noise. The L1 norm itself is small. The L2 norm is small. The number of comparators is small. The alphabet size is small. Not too many inactive pairs. The encoder is simple. The decoder is simple. Just a full list. It's a whole laundry list that always gets bigger and bigger as we sort of go into this. All right, so there are lots of topics I omitted, so this is pretty much one of my last slides here. There are sort of multi-reference portal codes, transition limiting portal codes, God knows what. There is all sorts of things about signal integrity. And obviously, the part that I omitted, which is really exciting, is all the electronics that goes behind it. How do you actually implement these things using electronic circuits? And one of the things that, I usually don't say that, but because this is because it was really the engineers of Candu who deserved it. We actually won the Best Paper Award of ICCC for our first design, which is big, because ICCC is the largest electronics conference in the world. Sort of and that's really something that actually is obviously not mine. I mean, I didn't implement that chip, but it's the Candu bus engineers who did that. It's really very, very exciting. All right, so you asked what does Candu mean? Here is Candu. So, a lot of people ask me, so how is it like? And I tell them, this is how it is like. So this is Sisyphus trying to take the stone and push it up the mountain and sort of push it back, push it back down again. I'm sorry. Come on, back. Not good. This is the problem with these things. Okay, I think I shouldn't actually do anything. Because it comes up on its own, no? Maybe not. All right, so what happens is, you know the story of Sisyphus, right? And really what it's, in order to do that, you must imagine Sisyphus happy. Otherwise, there is no way that you can survive this whole thing. Because, with all these things I told you, and it looks nice, right? There's this nice theory and nice implementation. But don't be fooled by that. I mean, I just cherry-picked the things behind it is much, much more complicated, and it has to do with people accepting things that they don't know. People who are trying to just put stones into your head, into your way, just because they don't want this technology to succeed. I mean, you have so many different things that you have to take care of. So it's really a Sisyphus work. And we will have this panel discussion today. I just want to say, if you want to build this system, the theory part of this, I used to say 3%. I'm saying right now I'm saying sub 1%. That's how much it contributes to it. It's really, almost nothing. But anyway, so I am actually very confident that we will have some success. And I think it's not because it's really because of the people who work in the company. And this is really good news. Thank you very much. By the way, the ISI ratio came from Ali Hormati. Where is it? Out there. Did I forget him? Oh, there he is. He actually was the one who invented that concept. There are actually a bunch of people from the but for the most part, they're from other places. Anyways, questions? Yes?
Can this kind of code be interesting to MIMO wireless channels?
No, I don't think so, because really the noise is different. It's different channel. It's really specifically designed for the same way that MIMO wireless channel codes are not interesting here. Yes?
So my impression was that you use converters because they are highly efficient in terms of the speed or the area that you take up from the chip.
Yes.
Is it the reason that you don't use any kind of channel decoding wavelengths?
Oh my God, you can't. I mean, look at how much time we have. I mean, it's absolutely impossible. Forget about any decoding algorithm. We have a few picoseconds to do our. It's not about nanoseconds. Certainly not about milliseconds. It's picoseconds. Anything. I mean, even the simplest thing, because you could actually reduce the number of comparators if you have sequential comparisons. So you make a first set of comparisons. Based on that, you make a second. Even that doesn't work because we don't have time for that. Impossible. Yes?
You try to encode also on several time slots. Not a lot of them, but 2 or 3.
So temporal coding.
Yeah, exactly.
Yes. Temporal coding, it is a possibility to do temporal coding. You lose rate, obviously. And just keep in mind, we cannot offer delay. So I mentioned 30 picoseconds, this is in 1. If you look at an end-to-end delay that we can tolerate in some applications, is in the nanosecond regime. So this is all we can afford. But then also keep in mind that the footprint of our circuit has to be incredibly small, which means if you actually have to take a lot of these things and work on them, the footprint becomes large and you're I mean, the constraints are just immensely. I mean, I couldn't believe it myself how tight they are.
Even 2 time slot is too much.
No, two is fine, but I don't know how you can actually do much better with 2.
The number of comparators is about the square root of the number of cycles.
It depends. The number of comparators in what you actually should compare it against the number of bits that you recover at the end, right? So the number of comparators that we do is actually in our current designs exactly equal to the number of bits that we recover. So you can't do better than that, but that's what we do. No questions? All right. Well, thank you.